I'm just making tea, and then I'll be ready. So feel free to watch cats, I guess. Oh no, there are no more cats. There you go, cats. What? Did you slap? When did you slap? What's your preferred type of tea? I usually like very fruity black teas, and also Earl Grey. Okay, tea is brewing. Good. Oh, what's Thor up to? Oh, what's going on over there? Oh, he's just walking. Okay. Look at that toast. Toast. Hey. Hello. Hey, toast. Okay. All right. I think it's time for trigonometry. Do we have... Let's see, camera. And... Okay, all right. Need to check if students are here. Okay, go for it. React. Show your presence. Ooh, triangular ruler. That's a creative React right there. Okay, cool. Oh, I was wondering why my computer was like running at full steam, but the game was playing, that's why. My turret was smoothly aligning across all of lunch. Okay, let's get started. I think it's time to expand our canvas. What? I know. Photoshop. Okay, cool. We're all here. Let's talk about trigonometry. Finally, we're going to talk about this thing that we call angles, and the ever-present sine and cosine functions that you've heard so much about. Probably already know of, but okay. So throughout most of what we've been talking about now, we've been talking about numbers on the number line, and it kind of like measures a position along a thing, right? And more specifically, it measures a position away from 0. Like we have some sort of concept of what the middle is, or what a default value is, or what kind of what the like we mentioned before, the identity value of numbers. In this case, for addition, if this is the position of something, then this measures a span of distance along a certain thing, right? And vectors kind of expand this concept to multiple dimensions. But now we want to measure something else. We want to measure something called an angle. And an angle is a different type of thing. An angle is something we measure between two planes, technically. And so these are just two-dimensional planes. In 2D, we also call them just lines. And so angles just determine what is the span like rotationally around a certain point. And that's what an angle is. And so far, we've been doing all of this without ever really talking about angles. So let's talk about angles and the many ways that we use them. And so let's do circles again. Oh God, this one has to be pretty good. This is the most important circle of all of the circles. You know what? I'm gonna accept this one. Close enough. Although I'm gonna want to rotate it. A little bit oval. Can I cheat? There we go. Okay, so we've been looking at vectors, and specifically we've also looked at normalized vectors. So normalized vectors, again, are vectors with a length of 1. And so what I've drawn here is the unit circle. And the unit circle is just all the possible vectors that have a length of 1 lie in the unit circle in 2 dimensions, right? So again, here we have 1, and here we have -1 on the x-axis. Then on the y-axis, we have 1, and -1 down here, and we have 0 in the middle. When we want to measure something that is not a position, but rather an angle, a unit for a type of rotation in a plane, we use many different methods or many different units to do this. So the one that you're probably most familiar with is the degrees, right? You've heard of like a 45-degree angle, right? Like you would say that this is 45. It is the diagonal, right? That's 45 degrees. This angle right here, when it's all the way from this line here. Oh, cat ears. Sorry. I forgot. I'm so sorry, Judith. That's why something felt wrong. Okay. And then we have 0 degrees is here, of course, when it's completely flat. So maybe we can erase a little bit of this. So we have 0 degrees, and here we have 45 degrees, and here let's just clean this up a little bit. All right, we have 90 degrees over here. And then if we go all the way to the other side, over here, we have a 180-degree angle. And then we have 270 I think. Yeah, I think it's 270. Okay, and so so this type of angular measurement goes all the way around, and once we're back to the beginning, we end up at 360 degrees. So this unit is called degrees. So if you, we use them a lot. We usually use them for like colloquial things. Like if we say a 90-degree angle, that's usually a right angle like this. And we've talked a lot about like right angle triangles and so forth. And so that's the most common unit that you've probably heard of. Now, we might ask ourselves, like, why is it 360? And it seems like it's not entirely known yet why, but one of the features of 360, like why this was chosen historically, is because it can be divided by a staggering amount of numbers evenly. So you can divide it by like 3, you can divide it by 4, like evenly without getting like weird decimals. So it's kind of a convenient number for that reason. Okay, so that's when we have when a full turn of the circle is 360, which again is kind of arbitrary, right? Degrees, then that is degrees. Okay, but there are other ways of defining this. What if instead of using this, there's another unit that you also use a lot. We just usually don't call it a unit, and that is a unit called turns. So if you say a half a turn, then what you mean is halfway around this, right? Half a turn is 180 degrees. A quarter turn is 90 degrees. So a turn is also a unit that you can use and that you quite often use in language, right? Boys, stop fighting. Okay, hold on. The boys are fighting. Hey, boys. No fight. Okay. Wait, Unity is also really weird about this. It shifted 90 degrees with 0 at the top. No, Unity doesn't have a weird shift like that. But I'm curious what you mean. Okay, so when the full circle is 360, we call that degrees. But then for turns, we start with 0, and then an angle like this would be an eighth of the circle, right? Because we divided it into 1, 2, 3, 4, 5, 6, 7, 8 different segments. So this would be an eighth. So 0.125, or more accurately, it would be 1/8. And this would be 1/4. And then we would have 1/2, or 0.5. And here we would have 3/4, and so forth. And then finally, when we get back to the beginning, we have a value of 1. So we can also measure angles using turns. And what turn says is that a full turn on the circle is the value 1, right? So if we say that we want to say 1 is a full turn, then we're using a unit, I don't know how to draw these arrows. Then we're using a unit called turns. And what's common to all of these is that they're cyclic. Like if you, like 2 in turns, if you go all the way around and then you go all the way around again at the value 2, that's going to point in the same direction as 0 or 1 or any other integer, right? Boys, they're fighting still. Or maybe they're playing. Maybe they're just playing. I think they might be playing, you know. It's hard to tell. They're mostly behind, so I don't know if you can see them, but... Hey. Don't body slam Thor. Okay, that's too much. That's too much. Hey. Thor? Hey. That's enough. That's enough, Toast. Goodness. Yeah, sometimes it's hard to tell if they're playing or fighting, but... The thing is that the kittens really like to play fight. And the kittens play too rough with Thor, our old boy. Hey. Okay, I'm putting Toast in quarantine right now. He's not allowed to fight. You need to chill your beans. Okay, Toast? Chill your beans. What? Salad! And now Salad is running after Thor. I'm sorry, my children are like this. That's the working from home mood. Boys, I'm trying to talk about angles. Is Unity using turns for anything? I don't think Unity is using turns anywhere, no. Again, turns is usually used for like colloquial things. It's just easy to talk about them, right? If you want to say a quarter turn, you're using turns. If you're saying a 90-degree turn, that's the same angle, right? Okay, I think the cats have calmed down now. Goodness. Okay, I think the kittens might be playing with each other now instead of playing with Thor. All right, cool. So that's turns. Actually, I feel like I should. We're making these blue. Okay. I know there's one final, well, there are many different ways of measuring angles, but there's one in particular that is a little bit magic that we're going to talk about next. As Thor is yelling in the background. All right. So these are, like, the choice of 360 can feel a little bit arbitrary, right? And then 1 is just kind of a number we pick because it's like easy, and it's like, oh, you have a nice, 0 to 1 mapping of the angle all the way around the unit circle. Boys? Okay. But then there is another way of measuring angles where, what if the number we pick for the full turn is a little bit more intrinsic or natural for the circle? So if you look at a circle, it has a radius, right? And the... Hey, Salad. Okay, I need to quarantine another cat. Hey, you are engaging in illegal activities. No. Okay. All right, so, so the radius of a circle, in this case, the radius is exactly 1 because we're working with the unit circle. And so one thing we might want to ask is that if we go 1 unit, it's a bit, hey, you need to stop chasing Thor. You can chase Toast. Just don't chase Thor. You're so full of kitten. Yeah, that's my tablet pen. Don't eat it. Okay. Boys. Toast and Toast and Thor are wrestling. Hopefully it won't get too ratty. I don't want them to actually fight with Thor because he's an old man. Okay, all right. Let's see. Where was I? Right. So we have the unit circle. It has a radius of 1. That's how we define the unit circle, right? But let's say that we want to go 1 unit of distance along the edge. So maybe we like what happens if we do that? If we take the radius and walk along the arc, using that radius, we end up somewhere here, I think. I forget exactly. This is going to be a little bit inaccurate. So what if we just say if we have a radius of 1, and then we set the arc to also have a length of 1, what if we just decide that this angle, whatever it is, we don't know what this angle is yet, but what if we just set this angle to 1? Like this angle should mean like 1 unit, right? And so this angle, where this measurement is 1, is called radians. So these are radians. Thor? Hey. Okay, now they're actually angry. Thor was growling. I don't know how to make them stop. Hey, boys. You need to chill your beans. There's some shit happening here. Okay. All right. So this is now a unit of 1. But with these, we've kind of defined like how we've defined the full turn. So we need to kind of calculate what that is. And so we can do that. And what we end up getting is that we can put several of these ones together. Then we end up getting something like this, where we have 1, 2, 3, 4, 5, 6 different segments, plus a little bit more. And so the final, like a full turn in radians, is a very special number that is somewhere around 6.28, etc. So this number has a lot of decimals, an unreasonable amount of decimals, in fact. So this is a way of measuring where, with radians, we have this number, 6 point something, very long. And that is kind of unwieldy to work with, right? You're kind of like, oh, well, 360 is kind of nice because I remember that number, but this number with an infinite number of decimals is kind of shitty, right? But this number actually does have a name, and usually we call that tau. So tau is equal to 6.28 yada yada. And what that is that this is the circumference of the unit circle. So if you have a circle with a radius of 1, this is simply the circumference if you measure it all the way around. This value is also, it's equal to 2 pi. Personally, I don't like using pi because you have this factor of 2 that makes everything ugly and frustrating. So personally, I always use tau because the nice thing with tau is that you can go between turns and radians incredibly easily. So if you want to know what a quarter turn is, you can just do 0.75 or 0.25, which is a quarter, and then multiply it by tau. And so if we now want to do the regular measurements we did before, then we start with 0, and then a 45-degree angle. So we have the diagonal. The diagonal is tau over 8. And then a 90-degree angle is tau over 4. And so this follows exactly the same way you would do with turns, right? So tau over 2, half a turn, and then tau multiplied by 3/4 is a 3/4 turn, and so forth. And then if you go all the way to the start, you end up with tau. And so this is what radians are. And the huge advantage of radians is that radians is one of the most natural way of measuring angles in math. Because of this special relationship where the angle is equal to the arc length of the angle, assuming you have a unit circle. So if the radius is 1, the angle is actually exactly the same as the distance along the circumference, or along this arc. And so that's kind of the beauty of radians, where if you know the angle, or if you know the arc length, going between the angle and the arc length is trivial. It's a very, very simple formula. And so, just to spell this out a little bit more. So if you have a radius r, and you have an angle, usually that's denoted using a theta, or an alpha. I usually like alpha because it's cute. Let's say we have an angle alpha. Let's color it. There we go. And then we have an arc length. So the length of this segment right here. I don't know. I don't like L. L is a bad letter because it looks like a 1. The D, I don't know. I don't know what to call this. Because we can't do A and alpha in the same thing. That looks annoying. Anyway, let's just call it the distance along the edge is D. So the arc length is directly corresponding to the radius and the angle in radians. So the arc length equals the angle in radians times the radius. And this is an extremely, extremely simple formula. Like, this is ridiculously simple. And this kind of goes through, like, this permeates through a lot of math. Anytime you look up any formulas involving angles, radians generally have the most simple or the most descriptive version because of this fact, because they have this very clean relationship between arc length and the angle. Okay, and so this only works if you're using radians. If you're not using radians, you're gonna have to add this like conversion factor. You have to add a bunch of conversions to convert to radians in order for this to become more simplified. And so this is a really, really nice relationship. And so because of this, radians is the default angle measurement. Whenever you're doing math, if it's not specified what angle or type of units it's using, it is almost certainly using radians. So radians is kind of the primary way to do angles in math. But of course, we still use degrees colloquially. So like if you're inputting a rotation for an object in Unity, you're going to type degrees into it, right? Because it is a little bit more intuitive. Like it's kind of hard to remember exact values when it's in radians. So usually, you for user input, you generally have degrees, or sometimes you can have turns as well, but usually it's degrees. But everything is just a factor of tau in radians. So in code, when you're working with radians, you almost always use tau multiplied by some factor, right? So again, a quarter turn is tau over 4, half a turn is tau over 2, 3/4 of a turn is 3/4 of tau, right? And so that's what radians are. We just define a full turn to be this very particular number that we call tau. Okay. All right. Any questions about this? Someone's typing. I'm gonna go get my tea. So fire up those questions. How do you calculate the trig function? That's complicated. In practice, most computers will use lookup tables and approximations. Those are complicated. I'm sure there's a Taylor expansion somewhere. Yeah. Here's the Taylor series for the cosine. So if you calculate this formula with an infinite number of terms, that is the cosine function. So that's how you write it, I suppose. But the thing is, it is kind of an infinite series, and so usually the function doesn't have a simple closed form solution. It is kind of an infinite series, and so usually we approximate it as best as we can. Yeah, but we haven't gotten to trig functions yet, but we're going to get there very soon. Okay. Can you tell us how to convert between degrees and radians? So they are off by some certain factor, right? So if you have your, let's see, if you have an angle in radians, and you divide it by, if you divide it by tau, then you're converting it to turns, right? So that gives you turns. But then if you also multiply it by 360, you get it in degrees. Because if your radians go from 0 to tau, if you divide it by tau, it's kind of like you're normalizing it, right? You're like putting it into the 0 to 1 range, and so this gives you turns. And then from turns to degrees, you're just multiplying by 360. So 360 times your radian value divided by tau, or just 360 divided by tau times your radians. So this is radians to degrees. Okay. So in practice, if you want to do this in code, so generally you just multiply either your radians or your degrees by some functions, right? So we can do this in the opposite way. So let's say degrees were white. Okay, so D is our degrees. So if you want to do this the other way around, it's basically just you flip the equation around. So then if you want to get radians from the degree value, you do degrees multiplied by tau divided by 360. Yeah, so this is how to convert between degrees and radians. And so this number, 360 divided by tau and tau over 360, both of these exist in unity. So in unity, if you have like my angle, this is a 45-degree angle. Also, here's a tip. Whenever you have angles in code, if it's in degrees, always specify degrees. Getting radians and degrees mixed up is really annoying, and it happens a lot. It's similar to dealing with like spaces, because effectively these are different coordinate spaces. They're just angular instead of positional. So I think it's important to specify whether or not something is in degrees or in turns or in radians. So if you want to go convert this from degrees to radians, then you take your angle in degrees and you multiply it by a constant that's in Unity's math library. If you can spell, there is a function called deg2rad, degrees to radians. Then there's also a radians to degrees. So these two constants, you just multiply by those, and you've now converted it to radians. Yeah, so these two, degrees to radians and radians to degrees, they are the same value you have for these two. And again, remember, tau is just a number. Like, this is just a number with a lot of decimals. We just use tau as a substitute because it makes it easier to talk about these angles, right? And so if I look at this degree to radians, we can just go to the code, and here we see the two different, the conversion factor, right? So degree to radians here, this is tau divided by 360, and this is 360 divided by tau. Yeah. Is there a spherical equivalent for a cone radian from the origin? Yes. Yeah, Joel just linked it. The steradian is the equivalent. Okay. Did that make sense? Any questions? Doesn't tau have infinite decimals? Yes, they are both irrational numbers. We'll need a lot of assignments on these topics. Sure. I can give you assignments. All right. People are typing. I'm gonna have more tea. I think the crucial thing to remember is that I mentioned it before, that again, using the word, like using the constant tau and the constant pi is all optional. Like the only real definition here is that the radians, a full turn in this measurement is this specific number, right? And so that's all radians are. They're just another unit. It's just that this number is kind of unwieldy to work with, and so it's easier if we like make use of these constants. Because then we're basically doing, instead of tau over 4, this is doing the 6.28, etc., right? Yeah, and this is a very like weird decimal number that's like a little bit complicated to remember, and so it's easier if we just use the constant tau. Okay. Is there a way to write tau in C# similar to math.py? Unity doesn't have it in their math library, which is really annoying. If you use my math library, then you do have it, but it's just 2 times pi. If you want my math library, you can get that here. It's very similar to Unity's library. Here you go. That one has tau, if you want, and a whole buttload of other things. If you want my math library, lots of spoilers in there, so don't read too closely into it until we're done with this course. All right, so that one has tau. The value of tau is 2 pi, and it's 6.28 something something. I don't know all the decimals. In fact, nobody does. But yeah. But it's probably good to know that, like, when you read about radians and equations and whatnot, most of academia and pretty much all of school uses pi, which I think is a bad idea because it adds this factor of 2, which is really gross. It makes it so that half a turn is pi, which is really confusing because this doesn't look like half a turn, right? But tau over 2 definitely looks like half a turn. And so 2 pi makes it very confusing, but this is what you're going to see in the real world a lot. But personally, for all of my projects, I've been using tau for 4 years, 5 years in all of my projects, and it's been wonderful and it's great. And so I recommend using tau. Okay. At least Shader Lab has a Unity 2 pi, yeah. Didn't even call it tau. Alright. I undid a line. Literally unplayable. There we go. Even C# has, C#'s math library has tau now. And yet, Unity doesn't. I would imagine using pi instead of tau is preferred because pi is used in many other places. Euler's identity would look awful without tau. No, that is not true. You are wrong. Euler's identity works with tau. It is actually completely fine. But maybe we shouldn't talk about imaginary numbers, but... so I think Euler's identity is e to the I tau equals 0. That's Euler's identity. I'm pretty sure, using tau. With, or no, it's 1, I think. Yeah, it's 1. I think with the traditional one is e to the I pi equals -1, I think. So, like, which one do you think is more beautiful? I don't know. Something like that. I forget exactly. I think it might be 0. One of them. So it basically looks the same, regardless if you're using pi or tau. Yeah, the real reason people keep using pi is because it's people have been using it. It's historically ingrained and we're kind of stuck with it, and most people give up and just use pi. And so that's the real reason. Okay. I'd really like to touch upon imaginary numbers next week. We could do that if you want to. Imaginary numbers are rarely used in games. They're almost never used. And the only use case, for the most part, is in quaternions. But generally, you don't ever really touch the internals of how quaternions work. Generally, you kind of treat it as a black box and just do things with them, and you're going to be fine. But if you want to, next week is going to be a lot more open. I don't have a plan for next week, so next week is fully open for either working on your own, or if you are, if you want like specific lectures on specific topics, I can improvise those. And so next week is going to be way more open. Yeah. So if you want, I could talk about imaginary numbers. They're just not super useful in game dev. But if there's no other like more important topic, we can absolutely talk about them if you want to. How do we decide what type of lessons we're having next week? So, well, I'm going to do that based on what you want. So if you're like, I really want to learn about derivatives, then we can do that. Or if you're like, I need to practice all of this, then we can just do like practical application of things. If you want to talk about splines, we can do that. And so it's kind of just based on what you want to talk about and a judgment call from my end in terms of what's useful and like what seems to be good at the moment. So, yeah. All right. Okay. I think practice would actually be best. Yes. My initial plan was to make the next week mostly just guided work. So I give you more assignments, and then I'll be present to help out rather than doing lectures. But we could do both. Like I could make it so that I can talk about esoteric, useless math to some people, and then other people can choose to work on other assignments. Again, I'm flexible. We don't really have a course plan, and yeah, and so we'll see. What are derivatives used for? Derivative just means rates of change, basically. So anytime you're dealing with like velocities, then that is a derivative. And so generally, derivatives are the analysis of the rate of change of something. Okay. Should we continue? I feel like now it became an open Q&A about random math things, which is supposed to be next week, not now, but... What's the chain rule of derivatives used for? It's when you have a function inside of a function and you need to do the derivative of that and need to differentiate that function. Okay, already feel like I want to go more in depth about this with radians and tau and show practical stuff because so far this isn't clicking with me, but I want to understand it better. Yeah, so like the use cases for this is exactly the same use case as for degrees. So far we haven't really introduced like a new tool. It's just a different unit, right? But we're gonna get into trigonometry now. Okay, so how are we doing on breaks? It is a pretty good break time. Okay, let's do break until 14. A little bit shorter than 10 minutes, but maybe that's okay. Okay, so I guess I can, I guess I can keep answering random questions during the break if you have any. Yeah, now the cats are not fighting. Now they're... Well, I see Thor is napping in the bedroom. I don't see the other two goobers. How does one calculate the point of refraction given a source target and the refraction index? I don't remember. Isn't that the Fresnel equations? I believe that is the Fresnel equations. Snell's law, that's the one. Okay. Yeah, so N1, N2 is the refractive indices of the material, or the two different media. Yeah, and then you have your angles here. And then you can just do some shuffling around to figure out the angles. Can Freya not see our chat messages? I am only reading YouTube chat during breaks, and now it's a break, so I'm reading the chat from my students for the most part. How do I calculate O if I have P and Q? Oh, the intersection point, or like where it's hitting the surface. That would be just a plain ray plane intersection test, which you can kind of like write that formula if you want to, and then solve it by hand, which is a little bit messy. I have that in my math library. In Unity, you can also do it using. Unity has a construct called a plane, which is really useful. So you can do new plane, and then you give this a normal and a point. So in this case, I guess it would be vector3.up, and then some point in the plane, which I guess we can just set to 0. And so Unity's plane function has a plane.raycast, and that is basically what you want to do, right? You want to send a ray into this plane, and then get which point it entered at, right? So generally you would have some sort of your initial light ray. And then you raycast using your ray, and then you get the distance along the ray out of it. So then the intersection points, oh, this is a curse name, is light ray dot get points at distance. So this would give you the that point. Well, if you have P, I guess. You don't need Q, then it's overdetermined. But you can do it from either P or Q. Oh, they used imaginary numbers for that? Okay, weird. Oh, that seems really cursed. Why would you do that using complex numbers? What is this about again? We're talking about refraction. When light rays hit a transparent surface, the light ray will change angle. And so someone asked about the angles. We're still on break for another 2 minutes, so. How would you make relative time in a game? Can you reduce game speed for certain stuff? The problem with that is going to be rendering and collision, because then you don't have a ground truth for one state of the world. Then every state is going to be relative to every position and velocity, which gets cursed. I don't even know how you would set that up, but I imagine it should be possible, and it also depends on how accurate it should be, and so forth. Okay. Okay, yeah, I feel like my solution is a little bit more clean than the imaginary numbers, but okay. All right. Then I think we're ready to talk about sine and cosine. Oh yeah, by the way, the plane struct is super useful. It also has you can project things to the plane. You can check which side something is on. So there's get side of a certain point. There's plane dot, I thought there was a project. Closest point on plane, that's the same thing as projecting. So you can get the closest point on plane from some other points. Has a lot of useful built-in functions. It's also a struct, which is very nice, so it doesn't allocate. So you can just like do very quick and easy operations with it. So that's neat. It's a useful type to have in your toolbox. All right. I think we're ready to resume. Why are shader developers against intelligible naming? The thing is that like the short names that you have in math and shaders, it's mostly because you tend to have, the focus is more on all of the operations together and being terse rather than the specifics, like the specific name of what something is. Because math has a lot of operations and usually not that many variables, whereas in code you have the other way around. And so math and by extension shaders do usually use quite short names in general, because otherwise your equations are going to be huge. So like this line is very long, right? But this is just a minus b, right? So if you type a minus b, this is way more readable, although you have to remember which is which. And so, but yeah, it's also a little bit of an artifact because variables in math tend to not have more than one letter in their name. Usually the way you solve it in math, I'm just going to slap it into this document because who cares? So if you have a math equation, the thing is that like if you have a lot of variables, you tend to name them with indices instead. So you would use like C0 or C1 with like subscript. So this is how you would generally do if you have like a lot of things. You just add a subscript, and then that way you have more variables. But in math, you basically never have variables with more than one letter. Yeah, and so basically just continue on like this. Just use letters, use subscripts whenever you need to, and so forth. Which, for better or for worse, math can become pretty unreadable because of this. But again, it's easier to see the structure when you don't have very long variable names. Yep, so it's kind of a trade-off. They both have their advantages and disadvantages. Anyway, trigonometry. I need to ping students again. Students. We're going live with trig now. Wow, React. Okay, React, we're doing the trigonometry, cosine, sine, cosine. Why use tab size 4 rather than 2? So much waste of space. Your comment is a waste of space. All right, let's do some waves. YouTube chat moment, yes. I'm so judgmental against YouTube chat. There are some YouTube chatters that are good. I don't want to say that all of you are bad. Not all YouTube chatters, as they say. Okay. All right. Now we're getting spicy. Time to do another circle. Rate my circle. Oh god, circles are hard. I wish circles were easier. Okay, that one's pretty good. It's a little bit of a potato, but that's okay. Can I like slightly adjust it maybe? I don't know. See how useful a unit circle is? We've been using this so much. Incredible, actually. Incredibly useful tool. Okay. We got our unit circle. So, the cosine and the sine function. Let's say you have a vector. We're just going to draw a vector on the unit circle, and we're going to call that V. How do you draw a V? I'm not sure. Like that, I think. Cool. And then, let's say you have an angle on this one. So, you know the angle here. And again, we're going to call it either alpha or theta. I don't know. Alpha is cute. And now the question is, what is the x-coordinate of this vector? And then, what is the y-coordinate of this vector? Because if you only know the angle, then you need to somehow figure out these coordinates if you want to convert it to a vector. Because an angle is just a number, and then the vector is it's two numbers, right? You have an x-coordinate and a y-coordinate. Like this, right? And so what the sine and the cosine function does is that it just gives you these two coordinates. And that's basically it. And so this is the cosine of the angle. And the y-coordinate is the sine of the angle. I don't know how to write anymore. I just don't. And so that's what the cosine and the sine is. Given an angle, the cosine gives you the x component of this vector, and the sine gives you the y component of that vector. And so what happens if you increase this angle? So you can just keep increasing this. What's going to happen is that as you traverse this circle, the cosine is going to decrease, right? It's going to decrease as the vector starts going all the way over here. But then as you come around to this side, the cosine is going to increase again because now the x-coordinate is moving to the right. And so this is effectively how the cosine and the sine functions are defined. And so when you look at the cosine function and the sine functions in a graph, generally it would look something like this, right? So this would be the cosine function. And then the sine function looks exactly the same. It just has a bit of a phase offset. And they have this repeating nature because no matter what you set this angle to, the vector is obviously going to return to the same position when you've gone a full turn around, right? And so that's why they have this repeating nature. If you go to, there's a super handy website. There we go. There's a super useful website called Desmos, which has a calculator or just a graph tool. This one is super nice whenever you want to visualize like simple functions. So if you haven't used this website before, very, very useful tool. Oh, I should probably do the default zoom and there we go, large things. And so if you do the cosine of x, you can now see that the function repeats itself. X is the input value and the y coordinate is the output value. And so this is the cosine. And if you notice, if you look at the input values here, it goes from 0, 1, 2, 3, 4. And notice where it stops here. Or no, sorry, I meant here, the peak here. The whole period repeats after exactly tau. Well, it says 2 pi because they're cowards. But you can see that it has radians as the angle because the x-coordinate is the angle and the y-coordinate is the output value, which is the x-coordinate of this vector, right? And so you get this repeating pattern after a full turn, and the turns, in this case, are measured using radians. And so that's why it's repeating after a value of 6.28, etc., right? So that's what the cosine is. And of course, we can add the sine function as well. And again, the sine function corresponds to the y-coordinate of this vector as we increase the angle. And so this is the relationship between an angle and the components of the vector. Okay. Did that make sense? Should I implement a practical little example so that we have some code experience with this too? Yes. Okay, what about 3D? We're going to talk about 3D rotations after this. But the thing about rotations is that rotations always happen in a plane. And so rotations are always planar. So it's kind of the only way to talk about them is in 2D. All right, so let's see, what am I? Right, we're gonna implement this. What do we do with this scene? Do I do a new scene? Okay, let's just do a new scene. It's probably easier that way. Or you know what? I'll just dump it in a parent object. There we go. So I want to do 2D view. I want to turn on the grid again. We're going to make a new script. We're going to call this trig test. I also have to tab back to Writer and then back to Unity in order for me to open scripts. I don't know why. So this is a little bit weird. Okay. So let's say we have an angle. Like we just want to input an angle. And this one is going to be in degrees. Let's start at 0. Oh, it's a float, actually. And then we want to give it a slider so it looks a little bit prettier in the inspector. So it's going to be 0 to 360. Then we're going to pull out our onDraw gizmos. Okay, so let's say we want to draw a vector based on this angle, so that we have a slider so that we can change the angle of a vector. That's it. That's what we're going to do now. And so maybe we can start out by drawing the unit circle. So that's a wire disk where vector 3.0 is the center and vector 3.forward is the normal and the radius is 1. Okay, just to get our unit circle going. Cool. And now we want to do something with this angular value. This one should draw a vector at that angle that we have as an input here. And so then we need a vector for that, and we're gonna call this v. Then we do new vector 2, and then the cosine and the sine function is in the math library of Unity. So cosine is the x-coordinate, so we'll pass the angle in there, and then sine is the y-coordinate, so we'll pass the angle in there. Now we have the vector, and now we can do gizmos dot, can do array, draw array from default to v. And that should be it to create our little rotating vector. Let's see if it works. So now we can set the angle, and now we did the classic example, the classic mistake that you always do. Something went wrong. Can you guess what happened? Class. Now I'm going to awkwardly ask class, and then they're going to have to like raise their hands and awkwardly... Radians, true! That is true. So we had our thing in degrees, right? But the cosine of the sine function accepts radians. So we need our angle in radians first. So angle in radians is angle in degrees times math dot deg to rad. And so there we go. We have our radians instead. And then we go back, recompile. Bip. And now we have a beautiful little angular thing. We have an angle of 0, can go all the way up to 90, 180, all the way around. And so there we go. It's a very, very simple implementation of this. And this, again, this could be anything. Maybe you're making a game like Worms, and you're currently setting the aim of one of the weapons of the Worms, like the 2D Worms games. Then you just increase or decrease the angle based on the keys that you're pressing on the keyboard, right? Or the controller. So that's a very, very simple way to go from an angle to a direction, right? Yeah. Feels like a clock. Yeah, making a clock using trigonometric functions. It's actually a really good assignment. Maybe I'll give you that as an assignment. Thanks, that's a good idea. Let's establish a Tau day. That already exists. So it's, I forget which date it is. Is it June 28th? Yeah. All right. So I think by far the most classic use case, for me at least, for the cosine and the sine function is just to convert from an angle to a vector. In fact, I usually use a helper function that does exactly this. So I usually make a function like that's called angle to direction. Then I pass an angle in radians. Then I just turn this into a function. Just return this vector. So now we can just do angle to direction. We pass in our angle in radians. And then there we go. So my math library has this built in, if you don't want to write your own. But yeah, so this is effectively a very, very, very common use case of the cosine and the sine function. Okay. Any questions about that? Did that make sense? No questions. It's either very good or very bad. One of them. Or a mix of both. Oh yeah, so this is a relatively new C# feature. This is called target typed new. In some contexts, the compiler can know what type this is, but generally you would do new vector 2 in that case. It knows what it is in this case because the method is returning a vector 2. Yeah. Okay. don't know if I should react to YouTube chat, but YouTube chat is being incorrect. And I don't know how to... I shouldn't respond. I shouldn't read it. Oh, jeez. But yeah, so that's why writer is graying out a lot of variables. Okay, so this is just a very simple use case. So like you mentioned, like if you want to make a clock in a game, you would set the angle based on time, right? So you would increase this angle just based on time times some value for how quickly it should move, right? And of course, you can just set this to a time value. So maybe we wanted to spin. Maybe you wanted to spin like one turn per second or something like that, right? So the way we would do that is that we want to set the I used the arc cosine of the dot product in the previous assignment. Yes, we're gonna get to that right after this. So if you maybe want to make this like spin 1 turn per second, then we could just set the angle in turns directly to your time value. So like, I guess editor application dot real time since startup times in startup. There we go. So maybe we have a time value here, and then we want to convert this to radians, right? And so we have to multiply this by tau, which is pi times 2. So now this one should move over time if we set our viewport to animate. There we go. There we go. What a beautiful animation. So now it's doing 1 turn per second. Yeah, so that's anytime we want to animate something in a circular motion, or you want to set the angle of something. It could be a, like, I don't know, we've been doing a lot of turrets. You can set it directly based off of angles like that. Yeah, so there you go. That's the sine and the cosine. All right. I don't think there are any questions about that then. Should I continue? Guessing? Ready to go to the arc cosine, or? I guess there are 2 more things we should talk about before we go to the arc cosine. So you have probably heard of a third function called the tangent. So the tangent of an angle. So what would the tangent of the angle be in this diagram? The name kind of gives it away, because the tangent of this angle is actually the length of the tangent to the circle at that point down to the x-axis. So this right here, the length of this one is the tangent of the angle. And so one thing that is a little bit weird about the tangent, I should remove this, is that if you move the vector like far up here, right? If you rotate it all the way here, then the tangent is going to go, it's going to become very long, right? So then it's just a very huge value. And as you hit pointing directly upwards, the tangent is actually undefined. The tangent sort of goes to positive infinity here. And then when you flip over to the other side, you get the same length here, except it's a negative value. And so the graph for the tangent kind of shoots off to infinity, and then it comes back from negative infinity. And so it looks a little wonky. So the tangent of x looks like this. As you can see, it kind of increases, shoots off to infinity, and then it comes back from negative infinity, and then it comes back there, and then it repeats the pattern. What are the use cases for tan? One of the most common use cases for all three of these is to solve triangles. And the reason for this is that all of these form different right-angled triangles. Because you can see that there's a right-angled triangle here directly, where one of the sides is the cosine, right? And then this one also forms a triangle, a right-angled triangle, and the tangent also forms a right-angled triangle here, right? This is a 90-degree angle, and this length is the hypotenuse of the triangle. Boys! And so one of the use cases for the trigonometric functions is to solve triangles. And so quite often you end up with situations where you have some right angle triangle, and then you know some things of this one. Maybe you don't know everything. Maybe you know this angle. So let's call that alpha. And maybe you know how long this side is. Let's call that, actually, let's call this theta. So if you know the angle theta, and then maybe you know the adjacent side, how long this side is, then you can calculate the other two sides using the trigonometric functions. And there are lots of different ways to do triangle solving. There's just a lot of them, but they all come back to this relationship right here. If you want, you can memorize all the different solutions to this. So if you don't want to do that, then I made a triangle solver because I'm lazy and I don't want to look this up every time. I made a triangle solver, and so if you click these, you can see that you can see how to calculate the rest of the information on this triangle. So I have this little interactive triangle solver, but you can see that you have all of the trigonometric functions pop up here, depending on what you activate or deactivate. Here's a link if you want the triangle solver. But the point is that you can use these trigonometric functions to solve for unknown sides of a triangle. Is sine cosine, wait, tangent is sine cosine, right? Then it shouldn't be shorter. Then shouldn't it be shorter as the angle goes upwards instead of longer? Well, so the tangent is the length of this one. So this is what the tangent function outputs. And again, if we increase the angle here, we make an even steeper angle, then the value of the tangent function is going to be the length of this long line. So then the value of tangent increases to infinity as we approach 90 degrees at the top. If that makes sense. But sine divided by cosine is smaller in that case. Well, in that case, I'm guessing it's the other way around. It's cosine divided by sine, right? I forget the... I forget which order it's in. Where's just the definition of tangents? Can't find it. It has opposite divided by adjacent. Yeah, that makes sense. Yeah, then it's sine divided by cosine. And sine is increasing up, it's approaching 1 and then cosine is approaching 0. So what tangent is approaching is 1 divided by 0, right? So sine divided by cosine is not smaller in that case. But yeah, I should probably also mention that the tangent can be defined using the sine and the cosine. So there we go. All right. And so what happens basically is I get a division by 0. And that's why it shoots off into infinity. And that's why the tangent of 90 degrees and the tangent of 270 degrees is undefined. But again, it's used in triangle solving. So anytime you have a right angle triangle, or even any triangle, and you just know a few of the angles, you can use trigonometry to solve for the other angles. Yeah. I thought the green line was sine. It is. It's just that the green line represents the y coordinate, not the length of the green line. So sine of alpha is the vertical coordinate of this line, but not the length of the line. The length of this line is cosine. So it's a bit of it can be a little bit confusing which one you're interpreting it as. And so it can go either way. Okay. Tangent is parallel to the y-axis. YouTube chat, shush. You can draw it in many different ways. This one is valid. Trust me. Do the math. Cool. Okay. So when you learn about this in school, you are endlessly solving triangles, and then you do nothing more. And that's kind of annoying, and we don't like doing that. It's kind of boring. And so that's why we use triangle solvers to not have to do that over and over again. But it's useful to remember that this is one of the use cases for the trigonometric functions. Okay, so now there's one more thing we need to talk about with regards to these functions. Math in general was tiresome like that. That's true, yeah. Okay, so let's say, oops. Just cleaning this up a little bit. Or maybe I should, actually, maybe I should just draw a new circle so we don't clutter this too much. Or no, I think we might be good here. All right, so let's say we want to do the opposite of this. So previously, when we were looking at the cosine function, sure, we know that the cosine of our angle alpha, that gives us the x component of v, right? So v dot x, or v subscript x. So with the cosine, we get the x component of our vector, and that's great. But what if we have the x component and we want to figure out what is the angle? Like, let's say we already know the x component of the vector, but we want to get an angle out of it. So how do we do that? Well, there's a very handy tool called the inverse trigonometric functions, where we can use that to shuffle things around as usual. We do algebra and move things around. So the inverse function lets us kind of cancel out the cosine function. And so what we get is something called the arc cosine. Usually you type it like with just an A. So arc cosine of v dot x. Let me just move that. You sometimes see it written as this. So you have cosine to the power of -1. So sometimes it's written like this. Both of them mean the same thing. This is the arc cosine. It is the inverse cosine function. And so we can kind of use our this coordinate. So if we know the component, we can get the angle out of it. And the one of the use cases for this is actually something we've done before. Because when we talk about the dot product, where is the dot product? Remember that when we had normalized vectors, we can actually use the arc cosine to get the angle out of it. Because then we actually have that exact use case. We have two vectors here, a hat and b hat. If we go back to our trigonometry here, those two vectors is the vector v and the x-axis. And so this, what you're looking at here, is the dot product, right? We're projecting v onto the x-axis, and that is the cosine of alpha. And so if we do the arc cosine of the dot product between the two vectors, we get the shortest angle between those two vectors. And this actually leads us to another definition of the dot product. Because this is not the only definition of the dot product. Let's scoot a little bit. So this one is a little bit more wordy, but I believe in you. So we have A dot B equals the length, I should probably do taller ones, the length of A times the length of B. It's a lot of vertical lines going on here. Should probably separate these a little bit. Times the cosine of the angle between them. So I'm just going to write that as theta. And so this is also a definition of the dot product. And so the dot product is actually very closely related to the trigonometric function. So there we go. This is a second definition of the dot product. And so the reason we can use it to get the angle is that if A and B are unit vectors, in other words, they're normalized, so we have these hats on top of them. If they are normalized, then A and B just have a length of 1. So this is 1 multiplied by 1, and that's the identity multiplication value, right? And so it just does nothing. And so if these are normalized, then A dot B is just the cosine of the angle between them, which is super useful. And so that's why we can then use this to get the angle. Because if we just have A dot B equals the cosine of the angle, then we do the arc cosine on both sides, and then we get the angle theta out of this. So we can erase that. Then we have our angle theta. And so this is a very classic use case of the dot product, just to get the angle between two normalized vectors, which I think is kind of cute that you can do that. Okay, did that make sense? I hope it did. A lot of people, whenever I talk about the dot product, like the first definition, what am I doing? My computer is acting up. Whoa. I'm still live, I hope. I kind of messed with the stream window. Degrees, angle, or radians? Generally radians. If something is unspecified, it's always radians. And so, radians. Yeah, so quite often when I talk about the dot product, why can I not draw anymore? I can't. It doesn't add anything to the canvas. I have my brush. Opacity is 100%. Okay. I'm just gonna reopen this document. Oh, I might have had a selection somewhere. Yeah, so quite often when I talk about the dot product, a lot of people want me to bring up this equation immediately. But I feel like this equation is really confusing unless you've talked about the cosine first. So that's why I kind of withhold. I withhold information from all of you. Imagine that. Because I feel like this definition only makes sense once you sort of know what the cosine is. Yeah, so that's the other definition of the dot product. And these two are exactly the same. You get the same results, like whichever one of these two you're using. Okay. And so if we want to, we could now rewrite our trigger function to use angles instead of using this like just the dot product result. Do you want me to do that on stream? Or, like, I don't know if you want, like, practical examples like that. Yes, okay. Seems useful just to reinforce the relationship. All right. Okay. Oh, then we can also fix the drawing of the arc. Now that we know about angles, because we had no idea what angles were before this. Okay, Unity, you need to stop rotating. You're stressing me out. It's been ticking in the background this whole time. Yeah, jeez. Should turn off the live update, so we don't need that. Okay. So let's go back to our turrets. Beautiful. All right, now we have two tasks. The two things we're gonna do is that we're gonna make this one use angles instead of using just the projected value of the dot product. And we're gonna make this one just draw the arc in front of it instead of drawing the whole thing. One thing to note though is that the way we've done it right now with the with this trigger, where is my trigger? There it is. One thing to note though is that the way we've set up the angular threshold right now is actually cheaper. It's faster to do it this way than to use angles. Just as a heads up. It's not like that bad depending on how many times you're calling this function, of course. Performance always depends on how much you use them, right? Excuse me. Okay, so instead of an angular threshold, we now want to use an actual angle. I don't know if we should call it actual angle or something else, but maybe, let's see, this is the field of view, right? So let's call it field of view. And this is in, let's see, do we do degrees? Probably degrees. People like degrees as an input. Oh wait, I can't write the symbol for degrees. They would make it very sad. Okay, maybe start at 45 degrees. Excuse me, my throat is sad. I've been talking too much this week. Okay, now it's an actual angle. Okay, now we have some errors because things are different. We have our gizmos. And so now we actually don't have our angular threshold anymore. We just have an angle in degrees. And so somehow we need to be able to recover our angular threshold. And so the way our threshold worked before was like this, right? We explicitly set the value of the threshold, and then based on that, we check the direction to whatever it is we want to check if it's inside or outside. But now, instead of setting this one directly, we are setting the field of view, right? And the field of view is usually, there we go. I guess that's negative x. The field of view is usually the angle here. So it's not half the angle, it's the full angle here. So that is our field of view, right? So if this is our angle, we need to figure out how long this is, right? And so we can actually use our trig functions to figure that out. So if you, let's see, I'm trying to figure out if I should make this, should rotate this or not. So one of the things we can do then is that if you imagine we cut this off here and cut our angle in half, we can use our half angle to get the length of this one. And as you can see, we're forming a triangle here. So again, we have a right angle triangle, we have half the field of view, and then we can use trig functions to get this projected value. And so I believe all we need to do is do the cosine of that half angle to get this the length of this one, which was our old value p. So we can make a property for that, angular threshold. So I believe that is the cosine of our field of view, and then we convert that to radians. And then we divide it by 2 because we want half of the angle, not the full angle. So I think this is correct. I could be wrong. So let's see if this works. Okay, so I think that might be correct. Yeah. So we can set it to 45 degrees. You can see that this is a 45-degree angle. We can set it to 90 degrees, and we now have a 90-degree angle. Then we can increase it all the way to 180 degrees. And so there we go. We converted it to angles instead. Okay. Any questions? Sorry for the messy scribbles. It got kind of tight in here. What was the other thing we were gonna fix? Oh yeah, the arc. We were gonna do that. Typing. Yes, we're gonna do only the slice now. All right. So now that we know the angle, I guess maybe we can do... We're gonna need the field of view in radians, so might as well make a property for that too. I like properties, they're very useful. Okay, so the gizmos, previously we were using the disk. So these are the ones that are drawing the full like circles on top and at the bottom. And so we want to draw the partial arcs of this. So we need handles dot draw wire arc. Okay. So let's see. We have a center, we have a normal, we have a from, which I'm guessing is the start of the arc. And then we have an angle, and then we have a radius. All right, so we are in local space here. And so the center is just going to be 0. The normal is just going to be up. The start direction, I believe, is going to be V left. No, sorry, V right. No. V left. So we're gonna move these because we need access to our vector. So V left is the this vector right here in local space, the direction that that's pointing, including the radius of that vector. So this is V left. So we're gonna use that as the start of our arc. I don't know if we need to normalize it. I don't know if the wire arc does that automatically. And then the angle, I don't know. This is actually in degrees. Okay, so Unity is using degrees here. Always good to look it up if your function is using degrees or radians. Ideally, all functions would use radians, in my opinion, but unfortunately, Unity is mixed. It's using both radians and degrees very inconsistently all over the library. For instance, angular velocity in 2D is using degrees, but angular velocity in 3D uses radians. Because fuck it, you know? Who cares? It's just... Nothing is consistent, and everything is garbage. And so you just have to get used to that and read the documentation all the time. Anyway, so we want to pass our field of view in degrees into this one. And then we need the radius, and that's just radius. And I believe that should do the bottom of that pie, and then we need to do the same thing at the top. Okay. And then let's recompile, see if this works. We did it! Look at this beautiful, beautiful trigger. Isn't this the best cheese wedge you've ever seen? It's great. Okay. All right. That's actually pretty satisfying to see. I know, right? It's really nice. Like once you see this nice little convex nugget, you're just like, yes, you just want to eat it. Okay. If you want the code, then here you go. How would you go about doing this in game view, line renderer? Yes, kind of. Sort of. The thing is, Unity doesn't actually have good tools for doing this in the game view. You can enable gizmos in the game view if you want to, but this is not going to show up in builds. So if you want to draw lines that show up in builds, then generally you would need either a third-party plugin for that, or you can draw shitty lines using gl.lines, and then you can push vertices to that, and like very manually draw lines using those. But they are always 1 pixel thick, and they look kind of garbage. But if you want a library to draw vector graphics, wow, imagine that. Then someone made a plugin called Shapes, which I very much would recommend if you want to draw vector graphics in Unity, like lines or arcs or circles. So there you go. But otherwise, built in Unity, you would use a line renderer or GL lines, basically, if you're not using anything third-party. Or make your own like shaders for that. But it's a lot of work sometimes, at least if you wanted to support a lot of features. Yeah. Okay. You know what? We should do our 10-minute break. So I'm actually gonna show you what Shapes looks like. So you can get a sense of what it does. So in case you didn't know, I've been working on videos for YouTube for a while, like educational math videos, and I make those videos in Unity. And so I made a custom timeline tool to make animations, and I have made a vector graphics library to draw these things. And so it's kind of like a janky video editor, except it's in Unity. And then all of this stuff is drawn using Shapes and TextMesh Pro. That's basically all I use throughout this entire video. So this start of the video is just explaining lerp, which I've already explained before. Yeah, and so this is my little video editing tool. And you can sort of scrub to any moment in this whole timeline. It is a very long video, and full of shiny animations and whatnot. But yeah, so this is a custom timeline. This is not Unity's timeline. This is completely unrelated to that. So it's a custom tool made specifically for making these animations. And so if you're wondering, how do I draw lines in Unity? What I do is that I use Shapes, which allows you to just draw lines, and it works in game as well. It's not editor only. It's just that I just do all of this in editor because it's convenient. Again, on draw gizmos is very nice, and so I do a similar thing for this. Yeah, and so that's splines, and yes, this is the spline video that I'm working on for so long. It is about an hour long. But yeah. Look at the splines go. So this is using splines for animations. Classic use case for splines. Is Shapes vector or SDFs? I don't know what you mean by vector in that case. You can make vector graphics using SDFs, which is what I'm using in Shapes. I use SDFs in many different places. But it's kind of the 2D SDFs. It's not the ray tracing type of SDFs. Because SDF is kind of a popularized term that means a little bit too many things now. But under some definitions, then yes, I'm using SDFs. Okay, so yeah, that's how you draw lines in Unity. Will you ever publish the tool? The timeline is only for me. I don't have any plans on publishing it. It is a hack. It is just leaking memory. It's just awful. But it's good for my use case because I'm just rendering a video using this, right? And so I don't have to care about memory leaks. Anyway, this is the outro of the video. Quick shout outs to NURBS because I didn't have time to elaborate too much on NURBS. And did you know that the color gradients are just splines in RGB space? So if you draw the RGB cube, that's a gradient right there. So if you're doing a gradient map in Photoshop, then that's just a spline. It's a spline in color space. Isn't that neat? I think that's super neat. I think that's cute. Okay. Anyway, credits. I'm not done with the credits. I need titles for these. But anyway, can you teach us to make a timeline like that? That is going to be a thing for your tool development course. So not a thing for this course. Okay. All right. Were we going to do a 10-minute break? I don't know when we were supposed to start. Do we start at 15:05 or I don't know? Yeah, I don't know if it's a good thing to have an assignment to make a timeline like this, because this took a very long time. Splines. Imagine that. Okay, yeah, let's do a break until 15:10. I didn't specify that earlier, but it's just doing that. YouTube chat is telling me to remove the ears. That tells you everything you need to know about YouTube chat. Jeez. I'm gonna have to, so I'm giving a talk pretty soon in Linköping, and they need me to shorten this to 45 minutes, but it's an hour long. So I need to cut out like a quarter of this. I don't know how I'm gonna do it, but you know, I'll have to figure something out, I guess. Why can't you upload an hour-long video though? Oh, for YouTube, I can do whatever I want. But for my talk that I'm giving at Linköping, it has to be 45 minutes. Okay, all right. Do I need to, I should probably go to the bathroom during the break. I will be right back. Boys, chill. Put it at 2 times speed. Okay, I'll be right back. Oh, sorry. Yes, I was muted. I forgot what I was saying. Oh yeah, so salad is like 5.3 kilograms, and he's 8 months old, and so he's not very old yet. So I think he's gonna grow up to be a big boy. And he's already kind of big. But there's a people say TM on the internet that it's actually impossible to overfeed kittens. And so according to the internet, he shouldn't be overweight. So apparently he can't be overweight. He's supposed to only be overweight if he's older than 1 year. So when he's an adult, I imagine he's going to immediately become overweight. Or maybe not. We'll see. Okay. Some shit happened in the kitchen. I'm just going to go check that out. It's hard to tell if salad is fat or fluffy. Yes. To all three. Yes, it's hard to tell. Yes, he's fat. Yes, he's fluffy. So I think it's a combination of everything, but also hard to tell. Okay, all right. I believe this is the final stretch, right? This is the last break. I think, according to, I forget what our schedule is. Where's my calendar? Yeah. All right. This is the last bit. We didn't actually have time to talk about a few things, but we could do that next week. So we actually have a few things I want to do next week. So that's good. All right. I have been a little bit more wordy today than I usually am, or during this course, than with the previous students. I think. I forget how I set up the other courses. I am very unstructured in my teaching. I don't have exact notes that I'm following or anything. For better, for worse. Is the stream lagging? Is it? Is it lagging for people? Everyone reacting with an Internet Explorer makes it look like it's lagging for everyone. But, okay, it doesn't lag for people. All right. Okay, just you. All right. Thor. Okay, Thora's opinions. That's okay. Final bit, let's go. We are finally going to talk about rotations. Okay. Oh boy. How do we approach this? So, in 2 dimensions, rotations are pretty straightforward. There are some, there are a few different ways we can represent a rotation in 2D. We can either do it using an angle, right? We can just have a single number that represents a rotation. Because if it's just 2 dimensions, all it takes is one number for us to represent a rotation. And when we talk about units, like I mentioned before, units are always relative to some zero, some center point, right? Some identity value. And angles is usually an angular measurement that deviates from the x-axis, right? So an angle of some value, right? What that means is a positive rotation that rotates it away from the x-axis. And so angles is just one way we can measure things in 2D, or store rotations in 2D. Another way we can store rotations is using basis vectors. We've already done this. So in 3D, we were storing basis vectors in a matrix, right? We have the x direction and the y direction, and then we can store that, and then from that describes an orientation, right? And so we can also describe orientation in 2D using vectors. So we can have it in vector form, and this would also describe an orientation because, again, this is a deviation from the x-axis. Okay, and that's all well and good. But in 3D, things get quite a bit more complicated. In 3D, if we want to store an orientation, the way that I'd like you to think about orientations is in terms of the basis vectors. So in Unity, we would have y up as our default. And then we have our 3 axes, x, y, and z. Right? We have y, we have z. That looks like a 2. That's better. So when you conceptualize rotations in 3D, I want you to think about this. This is what I want your mental model to be when you're thinking about orientations. And let's see. And so if you think about an orientation like this, sometimes you want to define a rotation from just a direction, right? So let's say you just had the red vector here. And this red vector is not enough to describe an orientation. Why? Well, because if you have a direction along this red vector, that still leaves a degree of freedom, because you still need to know what is the orientation around that axis, right? So in 3D, a single vector is not enough to, a single basis vector is not enough to describe a rotation. So matrices store all 3 of these. Technically, only 2 of them are required. You can calculate the 3rd one. And so when you think about orientation, have this in your head. Because if you're comparing rotations, sometimes you might wonder, like, okay, we have 2 rotations that are pointing in the same direction. Like if the blue arrow is forwards, right? they can point in the same direction, but even though they point in the same direction, they can have different rotations, right? Because again, you can pivot around a single axis without changing the forward direction of that rotation. And so rotations in 3D are quite a bit more complicated than just, you know, a single normalized vector that you interpolate, right? And so, like I mentioned, every single unit has some sort of center, some sort of default rotation. And so if one of these is the world rotation, so this is the orientation of the world, then what these describe, the other, like if you have an object in space, this one has to describe the difference between these two. Like, how do you get here from here? Like, given the world space orientation, how do we get here to the local space orientation? And so a lot of the different representations of rotations is all about deviation from that default orientation. Okay. And it's also useful because like this is what is stored in the matrix of each transform. They store these vectors. And you can use them to get orientations in other formats like quaternions. But these are kind of central to all of the matrix transformations that you do. Okay. And now rotations can be defined in many different ways. And so this one is kind of the basis vector form, or the like rotation matrix form, right? So we could call this a rotation matrix. And the reason we can call it that is because we can store all of these in a 3x3 matrix, just like we do here. So this part right here is the rotation part of the matrix. Now, incidentally, we also store scale there, but if it's a pure rotation matrix, the vectors would not be scaled, right? And so this part stores all of the orientation information. Okay. Sorry, my throat is very sad and I have to cough every now and then. All right, so this is one of the ways we can represent rotations. Then there is another format that I really like, called axis angle. Okay, so axis angle is another way to, again, describe a difference from the default orientation. So axis angle is stored in a single vector, which is kind of neat. This is one of the most compact ways of storing 3D rotations. It actually just stores them in 3 numbers. It's kind of like Euler angles, which we're going to talk about too, except not cursed. And so axis angle is basically a rotation described by a vector. And so the vector itself is the axis around which it's been rotated. And the length of the vector is the angle. And so what that means is that the longer this vector is, the more it is rotated around that very same vector. And the direction it's rotating in is according to the left-hand rule. So in this case, it would be in this direction, because again, unity is left-handed. So a very, very useful trick to do this is that if you... Wrong button. So if you hold up your hand, doing a thumbs up, if you do this using your left hand, then you can see that your thumb and your fingers, your thumb kind of forms a vector, like it's pointing upwards, right? Camera, come on, focus. It's not focusing. I need to hide sharp objects. So if your thumb is a vector, your fingers is the positive rotation around that vector. So again, use your left hand for unity, because unity is left-handed. The curl of your finger, of these fingers, is a positive rotation around this axis. So when you think about rotations, positive rotations around this axis always goes like this. And so we can use this as an example. If we want to know what direction does a positive rotation around x do, well, we can align our thumb so we can see that our fingers curl in this direction, and so a positive x-axis rotation is in this direction. Yeah. Okay. Is that why the rotation gizmo has different colors from the position gizmo? The x becomes green because it's rotating around the y-axis. They shouldn't be different. Not sure what you mean by the x becomes green. But the circle in the rotation gizmo is like around the plane defined by that vector. And so the rotation vector would basically... it's going to be real hard to draw a rotation gizmo. But the one that rotates in the YZ plane is around the x-axis, right? And the one that rotates in the XZ plane is the y-axis. And then similarly, sorry, I'm not streaming my screen. I'm sorry. Undo. Okay, so the x-axis, a positive rotation around the x-axis rotates like this, according to the left-hand rule, right? And you can visualize that rotation by kind of like drawing a circle like this, right? And so for the z-axis, it rotates in the xy plane in this direction. And so that's why that's in that plane. And then finally, the y-axis is a positive rotation in this direction. And so then that one is green. So this is usually how it's colored. Because the green disk rotates around the y-axis, the red disk rotates around the x-axis, and the z disk rotates around the z-axis. This is what I mean, the colors of the axes change. Right, so it doesn't actually change the colors of the axes. It's just that when you're viewing this in 2D, these circles flatten to just look flat. So the only circle you see is the z-axis. But then the rotation around the y-axis is a circle too. It's just that in your case, it's completely flat because you're viewing it side on. But what it really wants to show is this disk, right? Because it rotates around the y-axis. Yeah, so it doesn't actually change the colors. It's just that that's the way that it's visualized. And then that's how it looks, right? Okay. So that's why the gizmo looks the way it does in Unity. Okay, so in axis angle, the length of the vector determines how much we want to rotate around that axis. So if we have a shorter vector, it's not going to rotate as much. If we have a longer vector, it's going to rotate more. That was the... Wait, I did the wrong direction. I know my left-hand rule. Oh wait, was it the wrong direction? I don't know. Rotations are complicated. So if you have a long arrow like this, it would go further. So axis angle kind of encodes all of a full orientation using...
Hey, FutureGames nerds.
a full orientation using only a single vector. And again, the length of the vector is the angle. So, in other words, the magnitude of v, the vector, is the angle. And v hat, like as in the normalized version of this, is the axis. Do right-hand engines rotate in the opposite way? Yes, if you have a right-handed engine, they follow the right-hand rule. Okay. So that's axis angle. They're still rotating on the right side. Isn't unity left-handed? All of these rotate according to the left-hand rule. I don't think I drew any of these incorrectly. No, these are correct. Again, you can use your hand, do a thumbs up. If you do that using your left hand, the curl of your finger is a positive rotation around your thumb. And so with axis angle, if you want to rotate the other direction, because there's no way to have a negative length of a vector, right? That just doesn't exist. But so what's going to happen is that the vector is pointing in the other direction. And that is going to flip the direction it's rotating because now the axis has flipped and then the curl direction goes the other way. So for this one, it would go in this direction, right? So now this is the opposite rotation. And so this is axis angle. Okay. Does that make sense? What is that? Kind of lost with axis angles. Okay, let's actually. How much time do we have left? Because we could do a quick example. Let's do an example. You know what? I think I actually had a math animation of this that might help. Kind of like that. Yes. So that would be a vector pointing directly upwards. And then according to the left-hand rule, that would be a positive rotation for that ballerina. Oh, I found it. Okay. Here you go. Show it on stream as well. So this is how the axis angle representation works. We can describe the orientation of an object using this vector. So the longer the vector is, the further it rotates on that axis. So if we make it very long, it rotates further. If we make it very short or pointing the opposite direction, it's going to rotate in the other direction. So this is how you can describe 3D orientations using just a single vector. And again, the length of the vector is how far it's going to turn around that axis. And every orientation in 3D space can be described as a single rotation around a single axis. And so that's why this works. Isn't this how quaternions kind of work? Kind of, but not really. quaternions can be converted to and from angle axis relatively easily, but it's not directly how they work, no. But they're very closely related. What are the arrows supposed to represent? The arrows is the vector data of the axis angle. It's just the vector of the axis angle way of storing rotations. So it's just a 3D vector. And so axis angle. How did I jump to the background layer? Wait, I haven't been drawing on the background layer, have I? No. Good, close one. So axis angle is stored in a regular 3D vector. So x, y, z. So that's how that is stored. And then the rotation matrix is stored in a 3x3 matrix. What? There we go. Just so you have a sense of like what data is contained in either of these representations. What are the arrows supposed to represent? So the arrow represents both the axis it's rotating by, and the length of the arrow is how much it's rotating. So the longer the arrow, the further it's going to rotate. I hope that makes sense. In this case, the white one, yeah, like you did, it's saying is I'm just picking an arbitrary vector. It makes sense. Okay. It's kind of hard to wrap your head around orientation sometimes, so it might take a while. And that's okay. Things take time. What magnitude represents a full spin? That depends on which unit you're using. If you're using radians, then a magnitude of tau would be a full turn, right? If you're storing degrees in it, then it would be 360. So the angle is literally an angular value. So this could be like 45, and then that's a 45-degree turn. But usually you would store radians in this. In which case the magnitude of it would be, if you want to do a 45-degree turn, that would be tau over 8. Okay. Any questions before we go to the next way to do rotations? Should probably move this. Type, type, type. Words are being typed. In Unity, I guess it's degrees with a quaternion dot angle axis. Yes. So like I mentioned, you can convert between different representations of rotations. Just like how you can convert from an angle to a vector or a vector to an angle, you can convert between these two forms as well, and you can convert to quaternions. And so when you call the function quaternion dot angle axis, it's going to convert from angle axis to a quaternion. So quaternion dot angle axis. This one lets you pass in an angle. So if you give it an angle of, in this case, it's in degrees. So 90 degree, if you want a 90-degree rotation around vector 3 dot up. So this would give you a rotation as a quaternion that would be like 90 degrees around the up axis. So this would do that basically. And this could be any arbitrary value. So you can just pass in, I don't know, time, and then it's going to rotate over time. Or you can just have a static offset, and so forth. So using quaternion.angle axis will let you specify something in terms of the angle axis format, and then it will convert that to a quaternion. Okay, cool. We have 2 more rotation representations. Let's see, how much time have we got left? Not that much. Okay, so I'm going to continue. All right. Now we're going to do the shittiest one. All right. It's time to talk about Euler angles. Okay, Euler angles is one of the more intuitive ones. It's easier to wrap your head around. And it's also one of the worst ones because it suffers from a few problems. Okay. So Euler angles quite often isn't actually Euler angles. If you want to be super technical, Unity uses something called Tate-Bryan angles. But the idea of Euler angles, let's just steal this one for a moment. What? The idea of Euler angles is that instead of specifying a vector or like 3 vectors, in Euler angles you specify 3 different degrees around certain axes. And so what you specify here is a rotation around some axis and then another axis and then another axis. I'm not entirely sure what to call these values. Maybe I'll just call them alpha and beta and gamma. I forget what gamma looks like. It's like a weird Y, I think. Something like that. I forget. And so these are all angles. So I'm just going to add a little angle marker, pretending they're in degrees specifically now. RBG, yes, because I'm not using my axis colors intentionally, because these don't actually correspond to X, Y, and Z. So Euler angles, well, they can, but in Unity they don't. Let me just bring up my notes because I always forget the order. So Unity's angles rotate in a very specific order. So if you imagine starting from, let's see, your identity rotation, as in no rotation at all. If you start out from some state, right? So the way that Euler angles work, and the way that the specific one that Unity has implemented, is that they use the order of rotation is specifically Y, X, and Z, using the intrinsic angles. In other words, around the orientation itself. So if this is no orientation, then if you specify Euler angles of 45 degrees, then it's first going to rotate 45 degrees around the y-axis. And then maybe the second one says, I don't know, -3 degrees. Then that's going to rotate around the x-axis, like a tiny bit, like that. And then it's finally going to rotate around the z-axis by a specified amount. So Euler angles basically let you specify specific angles that you want to rotate in order around certain vectors. So unity, again, specifically does y first, and then x, and then z. That's how that works. And so specifically, unity's implementation of Euler angles does the order of y, x, z. Which is kind of weird, but it's actually kind of the most useful order, especially for games where y is up. And yeah, so Euler angles, they do consecutive rotations around each axis. And so I don't even know how to draw this, but it's doing the y-axis first. So it's doing some sort of alpha rotation. That's the wrong direction. So alpha. And then it rotates around the x-axis. That's not the color for x. Or wait, I need the color for beta, so that's correct. And then finally we had our gamma. And that rotates around the z-axis. Okay. And so specifically, it rotates in this order. First around the y-axis, and then around the x-axis, and then around the z-axis. And Euler angles in unity is what you see in the transform component. So when you look at a transform, we just have an empty game object here. You can see that it has an orientation, right? So now watch what happens when I increase the rotation on the y-axis. You can see that it's turning specifically around y when I increase this angle. And like I mentioned, unity does the order of y and then x. So if I increase x, you can see that it's now rotating around x. And then if I want to rotate around z, I edit z, and now it's rotating around the z-axis. It specifically works like this because I edited them in this order. But if I now turn or change the y value, it's going to be a little bit confusing to interpret this, right? Because now they're kind of wonky. And so it's really hard to wrap your head around Euler angles, except when you just have a very simple orientation. Because it has this like cascading effect of doing one and then the other and then the third, right? The biggest drawback with Euler angles, though, is that it's actually possible to lose a degree of freedom. And this is something called gimbal lock. And specifically, this happens when you set... There are a few edge cases where this happens. If we set the rotation on the x-axis, if we set this specifically to 90 degrees, so we type 90 in there. Now, what happens is that if we rotate around the y-axis, this is what happens. And if we rotate around z, this is what happens. So you can see that the second angle and the third angle actually do the same. And so we've lost control over those two. We have to make x deviate from that before we can start like finding new orientations from that point onwards. And so that's what gimbal lock is. The term comes from like a physical object called a gimbal, where you can get into this state where you have this situation where two axes collapse into the same axis. And that's what's happening here. And that is bad. I believe there's been a space shuttle accident that was caused by gimbal lock, right?
What?
Wasn't there a space shuttle accident, or maybe not a shuttle, but something space related?
Apollo hit gimbal lock a few times, but they were able to recover. But it kind of fucked them up for a bit.
Okay, so gimbal lock fucked up Apollo for a bit. So this is a legitimate problem sometimes. You had to realign from the stars through the window? Oh, yeah.
Not through the window, through a special device, but yeah.
Through a special device, not a window, according to Ashley. Ashley is a space nerd, so she knows these things. Anyway, gimbal lock, not a good time. We don't want that. So that's what Euler angles are. The use case for Euler angles is usually just for typing in numbers. That's kind of the only thing that Euler angles are good for. Otherwise, I generally prefer the other ways of representing rotation because Euler angles have this weird process of doing one rotation after the other. It's very sequential, right? Yeah. And so just to show the order, so if you want to get super pedantic about this, there's a difference between intrinsic or extrinsic rotations. So intrinsic is rotating around its own axes, and extrinsic is rotating around the world space axes. In other words, the original orientation. So unity is using intrinsic axes of the order y. I'm drawing a prime there to denote intrinsic. It is y, x, and z. This is actually the same thing as doing extrinsic rotations in the order of z, x, y. So if you want to read up and nerd out about Euler angles and take Bryan angles, this is what unity is using. So there you go. This is the order of rotation around the axis in which it rotates around. Okay, so that's Euler angles. They're kind of annoying, but they exist. They're always in the inspector, lurking around, and so we kind of just have to accept them. Okay. Finally, we've gotten to the final boss of 3D orientations, and the final thing we're gonna have time to talk about today. And that is quaternions. Quaternions? I've heard people pronounce it as quaternion. I don't like that pronunciation, but I don't know which one is correct. Quaternion. Okay. Whew. Quaternions are stored in 4 numbers. What are you going to call them? X, Y, Z, and W. All right. So quaternions is stored in 4 floating point numbers. So it stores one more number compared to Euler angles and axis angle, but it doesn't store as many as rotation matrices. Rotation matrices have a lot of values. All right, quaternions. The biggest problem with quaternions is that they are very hard to visualize. Quaternions sort of have this problem of they either have to be interpreted in 4-dimensional space, or you have to interpret them using geometric algebra, which introduces a shitload of additional concepts that are really hard to wrap your head around and that I definitely don't have time to talk about. And so usually, the way that people use quaternions is kind of as a black box. Like you have a box of magic that is just like math happens in here. So you have some representation. Maybe you have angle axis, you pass it into a quaternion, and then maybe you do some operations using the quaternion, and then you plop out a matrix from it. This is how most people use quaternions. Most people never learn what's going on in that box. I would argue that most people who implement like quaternions in game engines probably just copy and paste some code and just accept that it's going to work the way that it does. And so quaternions are complicated for that reason, because the math inside of this box is very counterintuitive and very strange. And I know that's a bit of a frustrating answer, so I'm going to give one more little indication of how this works. Let's see, I need to... where are my notes? Okay. I just had to pull out my notes. You know what? Maybe I'll just do this. So the relationship between quaternions and angle axis is very, very intimate. They are closely related to each other, but they are not the same thing. And so here you go. Here's how they are kind of related to each other. This might be difficult for you to read if you don't know like complex numbers and whatnot, but effectively there is a vector part to this. That's what you're reading here on the right. Let's actually invert this, and let's that's fine. Need to brighten this up. Love those pixels. Looks great. And so these kind of correspond sort of to the different components here that you have. And so if I do that and then that, so this is the so this here is the x value, and this is the y value, and this is the z value up here. So the x, y, z are these three numbers multiplied by sine of the angle divided by 2. So if you assume an axis angle formulation, this is what the relationship looks like. And then the number here, this right here, that's w. So that's w. And then half of the angle multiplied by the x component of the axis is x. And so they're closely related to angle axis, but it's not quite the same thing. So you can convert between quaternions and angle axis relatively easily. Okay. And so if you want to recover the axis that it rotates around, you can get that by normalizing this as a vector. So if we call this v, let's hide this mess. So this up here is v. If we want to convert this to angle axis, then I don't know what it is, but Google now gave a link to that site, which is a site about not using quaternions. Yes, because they argue that we should use the geometric algebra approach, which is basically the same thing, but you phrase it in a different way. So that's not about not using quaternions. It's about using the geometric algebra equivalent to it, which is the same code in the end. Okay, so if you want to recover the angle axis formats of quaternions, then the axis is the normalized version of v, and the angle the angle is 2 multiplied by a function called a tan 2, and we pass in the magnitude of v, and as a second component we pass in w. So as you can see, quaternions and axis angle, they're not the same thing. They are different. So it's very important to keep that in mind, because if you treat this one as an angle axis, you're going to get the wrong results. Okay, but then you might wonder, why? Like, why do we have this weird, like, complicated math box? The only reason we use quaternions in games is because they composite very well together. So if you have one rotation around some axis, and then you want to rotate around a different axis after that, so in other words, you want to composite 2 rotations, then multiplying rotations together is very fast using quaternions. So what's really cool about quaternions is that if you have a rotation, let's call it q for quaternion, so q1, if you multiply that by q2, you get the rotation that is the same as doing q1 and then q2. And so compositing rotations using quaternions is really fast. And by extension, interpolating rotations using quaternions is also very fast. So we use quaternions because interpolation and composition is fast. Other than that, they are the least intuitive and the most messy way to think about rotations. And so most people use them like this. Most people go to Unity, and then they're like, okay, I want to rotate something. So if you have a rotation, that's like, okay, maybe we do Quaternion.Euler. Maybe this is the rotation we want. And then we have another rotation. Maybe we want to specify this one using angle axis. So I want to do vector3.right, and I'm going to rotate like 60 degrees around that. Oh, sorry, stay the way around. And then I want the rotation that represents the combination of these two. Then we can do that by multiplying them together. So rotation A multiplied by rotation B. Okay, and so this is kind of the beauty of the quaternion, because you can just multiply them, and the fact that you can composite them like this makes them very useful. And it's also useful because interpolating them is fast. So we have the quaternion.slurp. Slurp is really fast for quaternions. If you wanted to do this using rotation matrices, that would be much more costly. And so we are kind of in this unfortunate situation of having to deal with this complicated construct called the quaternion in order to represent rotations that are computationally efficient, right? And so, again, you don't have to learn how quaternions work in order to use them. Just remember that you can composite rotations and like add them together like this. Another useful thing to remember is that quaternions have inverses. So you can get the opposite of a rotation using quaternion dot inverse. So you can get the opposite of a rotation. And this is basically all you need to know about quaternions in order to make use of them in game development. You can go 10 years in game development and never know how quaternions work internally, and you'll be fine. And I know that because that's what I did. And so the internals of quaternions are messy, it's complicated, and most people who even implement quaternions probably just copy-paste code and trust the math. The math behind quaternions is really fascinating, but it is mostly useless. And so I'm not gonna talk too much about that. Probably not at all, unless you really want me to. I can do that next week. But this is basically all you need to know. Oh, and also, you can rotate a vector by a quaternion if you want. So if you want to rotate a vector using a quaternion, you can multiply a vector by that rotation. Sorry, other way around. So you can multiply a quaternion by a vector, and then you get that vector rotated by that quaternion. Yeah, and so this is kind of like all the tools you need to use quaternions. Okay. Any questions about that? I know they're a little abstract, but that is kind of intrinsic to the way that they work. They just are. I can't draw a four-dimensional diagram, and going through all of the geometric algebra, which is the stuff that they're talking about in that article that you linked, I don't have time for that today. Yeah. Why is the result of vector multiplied by quaternion a vector? Because they decided that that's how you write that syntax. It is, yeah, basically that. I think in technically, it's not actually multiplying them together. I think it's doing a sandwich product. So it's a different thing, but yeah. Is Q multiplied by V the same as V multiplied by Q? No, because a vector times a quaternion is not valid. And so you have to do it in this order. When it comes to multiplying rotations, these are A times B is different from B times A. So doing rotation, like compositing rotations like this, is order dependent. In other words, it's non-commutative. Yeah. So you can kind of intuit that. Can show you what I mean. So if you consider rotations, where do we go? There we go. We got two rotations. So let's say you want to rotate around, come on camera, focus. Let's say you want to rotate around the x-axis and the y-axis. And you want to do it in 90-degree increments. So if you do rotate around the x-axis 90 degrees, and then you rotate around the y-axis 90 degrees, that's going to do that. And then you flip it. So now we do x-axis on this one and y-axis on this one. So if we do x-axis here, we're going to get that. If we do y-axis on this one, we're going to get that. And so now these two are different orientations, right? So depending on which one we pick first, we're going to get two different orientations. And so the order in which we apply orientation matters, because these now point they're just different rotations, right? Yeah, and so keep in mind that rotation multiplication, or compositing rotations using quaternions, is order dependent. So it doesn't work like, with math, where you can do 5 times 2 is the same as 2 times 5. In this case, it's different depending on the order you do it in. Incidentally, this type of compositing, where you take a quaternion multiplied by another quaternion, you can composite matrices the same way. If you multiply matrices together, you get the combined operation of that, which is very, very powerful. And it's not just for rotation matrices. You can do that using the full transformation matrix as well. If you multiply two transformation matrices together, you get the combined operation, which is used a lot, especially in rendering, where you have a lot of combined matrices. Okay. I'm running late. We are technically, I think we're out of time. I think that's all. Someone asked if you're gonna have assignments using quaternions. Yes. You're gonna have assignments that make use of rotations, but you don't have to learn about quaternions internals, because again, this box, nobody likes to open this box unless you're really excited about math. And so you also don't really need to open it, which is nice. So you don't have to learn about the four-dimensional cursed nightmare that is quaternions. Okay. Pandora's box of maths? Yes. Yeah, if you've heard of complex numbers before, quaternions is basically an extension of complex numbers. Instead of just having a constant I, you have another one called J and another one called K. So you're kind of expanding it to have even more imaginary units than just one. Yeah, it's a whole thing. Are there really people who are experts on quaternions? Oh yeah, definitely. Are there any this edge case will screw you over, or is it just like multiply them together and trust the process? Generally, you'll be safe if you use the built-in functions for quaternions. There are some edge cases like for example, if you want to recover the axis from a quaternion, it's possible to have a quaternion where the axis has 0 length, and you can't normalize vectors that have 0 length, right? Because it's effectively dividing by 0. Because remember, normalizing a vector is the same thing as dividing by the magnitude, right? So if the magnitude is 0, then it's a division by 0. Okay, and so basically, if you have rotations that are very close to 0, you might run into division by 0 issues. But if you use Unity's built-in functions, I imagine they already take care of that case. So yeah, let's see. I don't know if they have a function on this one, but I think so. Yeah, 2 angle axis. So you can convert this one to an angle axis format if you want to. And I presume this one is safe. So you can just convert directly to it. What's the schedule plan for next week? Good question. Yeah, because technically it's a weekend. And so you're not supposed to have assignments over the weekend. I guess it depends a little bit on what you prefer. There's only one more lecture of things I want to talk about left. So let's see, what could we do? So I think I'm flexible next week, but I'm not sure about Ashley, and I'm not sure about you, if you have anything planned next week. How's your next week?
I just have to meet on Wednesday. Can do whatever.
Okay. So we should definitely have a lecture on Wednesday. Yeah, because I do want to give you assignments, but I don't want you to work on them over the weekend. But it might be nice if some of you want to. So I guess we could move Monday's lecture to Tuesday? Maybe? And then you could work on Monday on your own. I don't know what your calendar looks like, and I don't think I can move things. But is that cool across all the different sites? I don't know if you have anything else planned on Tuesday. Wasn't it already Tuesday, Wednesday, Friday? Just the previous week. Usually I do Monday, Wednesday, Friday. Stockholm should be fine next week. Won't that make it 2 back-to-back lectures? Yes. But next week, I think we're gonna mix things up a little bit. I think next week I want to give you more time to work on assignments, and I also want to do a little bit more optional lectures. Lectures that are like things that might be fun to talk about, but maybe not all of you want to. And so I just want to kind of like explore a few topics that might be useful. There's only one crucial lecture left that I want you all to join. Okay, but I think if we move Monday's lecture to Tuesday, I think that would be good. Because I don't want to force anyone to work over the weekend. What do you think? Is that good? Is everyone okay with that? Okay, looks like okay. Looks like we should move the lecture. Okay. Then let's do Tuesday next week instead of Monday. And yeah. I think that should work. And then on Monday you're gonna have lots of time to work on the assignments. So another thing I can do is like I can split up my time so that I don't only do lecturing, and I can make it so that I'm available for mentoring while you're working on the assignments, instead of doing lectures. I can do that too, because I want you to have time to work on your own work on the problems themselves. And if it's helpful to have me around, that might be a good thing. So these blocks don't have to be lectures. Just whatever you think you need the most. But yeah, so let's do Monday, you work on your own. Tuesday, I'm going to do the last planned lecture. And then the rest of the time, we can figure it out as we go along, like what you want to do, basically. Either I can improvise some more lectures, or if you have topics you want me to talk about, I can do that. Or I can just supervise as you work on your own things. Is there a place where we can put some wanted optional topics to discuss? I don't know. Is there a class representative that would be ready to collect things from all the students? You did. You are now responsible for this. I'm shoving it onto you. It's your that's your task. That's your assignment. Okay. Just any topics that you might think is interesting, or something we want to know more about within games. I don't know if it's complex numbers, or you want to know the black box of quaternions, or if you want to know about splines or stuff like that. The one thing we have left to talk about that I really want to talk about is interpolation, oscillation, and motion. and frame rate independence and player movement, which is kind of like point physics, and talk about trajectories. Those are kind of the 4 mixed bag of topics we have left. And so those I'm going to talk about on Tuesday. So that's the plan. They all sound extremely necessary too. Well, everything is extremely necessary, if you put it like that. Okay. All right. You have the thread. Good. I'm relying on you to organize all of this. And yeah, I guess that's it for today. We've gone a little bit over time. I hope that was okay. And I'm sorry if someone had to leave early and missed a few things. I'll also send you this document. Maybe I can do this one separately. Oh no, this one is too big. Will you be available to have time for mentoring too? I think so, yes. Again, I dedicate most of our class time to lectures, but I think it would be helpful to have at least one day of just mentoring. I think maybe we can do that as the last day. At least one of the days, I think. And so I think, yeah, either Wednesday or Friday is going to be a mentoring day, I think. All right. Any non-lecture day? Yeah, we could have a day that has no lectures at all. Or we could do lectures in the beginning of the day, and then the rest of the day is just working on your own. I am flexible, so I can do whatever you want, what you think would be best. Okay, well, that was this week. You did it. You made it through all of this. We have now speedrun math up until a select section of high school math, up until parts of university math, I think. Okay, I'm gonna save this. So you get to have your whole thing. Math class 2022. Shout out to YouTube chat. How's YouTube chat doing? YouTube chat is always confused. There's so much confusion in YouTube chat. Thanks for the amazing lectures. Well, thanks for joining. I'm happy you, well, hopefully learned something from this. If you feel like all of this is kind of overwhelming, keep in mind that this is the kind of stuff that you study for years in school. And so keep in mind that it can be hard. It can be daunting. We're going through many, many, many topics in a very dense way. And so I hope you don't feel too scared. And it's okay if it feels like a lot, because it is a lot. Okay. All right. I should send you all the diagrams. Excuse me. There you go. These lectures were fun. Good. That's good. I'm happy. Managing to make math lectures fun. I'm really happy I was able to achieve that. Okay, is there any code you want from this? It's kind of spread out into many different files now, so it's a little bit messy. Maybe a GitHub? Sure. Do you want my turret as well then? I can put the entire project on GitHub. If you want my Unity primitive turret. If you want this little nugget, okay. I believe that's the scene, right? I don't know if we should include. Okay, I think that might be my test code. Yeah, let's delete that. We don't need that. We don't need that. Okay. Sorry, I'm just cleaning up the project. I have nothing else to do, so I'm just gonna hang around here, even though it's overtime. Feel free to leave, the class is over, but I'm gonna exist here for a bit if you have if you have any questions, I guess. I'm just setting up the project so I can send it to you in a more clean way. Okay. Okay. I think this is clean enough. I have a few like random scripts lying around, but that's okay. Let's just make sure this works. Yep. Definitely pose a weekend Kyle's problem. Wait, what's that? Weekend Kyle's problem? Do you want an assignment over the weekend or? The opposite of that. You want me to solve an assignment for you over the weekend. I'll be doing a summary doc writing of the notes, so it's searchable, but that's for Monday. Okay, cool. All right, okay. How do I guess I should put this up on GitHub. I'll do that off stream. I don't want to accidentally show passwords or something. And then I will send this to you, so you have the whole thing. Save. All right. Is there anyone who wants assignments over the weekend? Like, should I come up with something? Or should I not? Maybe something small. Well, one of them we already know, because someone asked in your chat. One of them could be draw a clock in using gizmos. Just draw a clock that shows the current time. There you go. That's a small one. As in, it should it should have a second thing that like ticks for every second. Jeremy Wright in YouTube chat would like to say, no, don't do that. People need to focus on their lives during the weekend. Everyone is overworking themselves for nothing. Yeah, Jeremy Wright would like to make it very clear that you shouldn't work when you shouldn't work. So I'm sorry, Judith. You're not allowed to do the clock. Even though you're excited to do it and you have nothing else to do, you're not allowed to do it because that's work over the weekend. I'm really sorry, but I'm gonna have to retract that assignment. Do the other pointers need to move as well, or just the seconds? No, you should do all of them. All three. I mean, you can go even further. You can draw the arrows for like the months or something as well. Maybe that would be good. Just do a clock that has like a ridiculous time span. You can do another one that rotates really quickly for each second, so you can see the milliseconds. But yeah, I'm not expecting you to work over the weekend. You have all of Monday to work on stuff. And so I might try to come up with some simple like assignments for you to do over the weekend if you want to, but I'm not expecting you to do any of that over the weekend. Just in case you want and you have some extra time and you want to do it, then feel free to do it. But most of the assignments I'm going to do for Monday. And so I'm probably not going to have all of the assignments ready over the weekend, so it's probably just going to be on Monday. Yeah. Okay. Speaking of, shouldn't work when not working. Isn't this lecture over? Yeah, it is over. I'm not here. Okay. All right. You'll need to see something cute before we leave. Look at those two. Stop focusing on the mic. Look at them. They're napping next to each other. Aren't they cute? I love them so much. Especially because they love each other so much. It's adorable. Okay. I guess that's it. Unless there are any final questions. Any last thoughts? Before I go? I don't even know what I'm gonna go do. I kind of want to take a bath and just do nothing for 5 hours. Oh, where'd you get your gizmo toys? I made them myself. I 3D printed them and I painted them. And yeah, I also 3D modeled them back when I had a Maya license, but I don't have that anymore. Thanks for the new background. Oh, heck yeah. Nice. Blender better? Yeah, I know. It's just that I used Maya back when I was doing 3D art. My plan is to do a stream where I try to learn Blender live, where people can judge me and also help me. I'm thinking I can have like guests on over voice, and then I can get some live guidance, because like I don't need to learn how to do 3D modeling. I just need to learn how to use Blender, right? So I think I'm gonna do a stream where I'm just learning Blender. Let's do that on Monday. I mean, Monday, you were supposed to work on your assignments Monday, not watch my shitty stream. But I guess you could have it on in the background. Maybe I should do that Monday. I keep saying I should do this, but I never go through with it. So maybe Monday is the day. If I do so, I'm gonna do it on Twitch, because I don't think it's a YouTube-worthy stream. And so be sure to follow me on Twitch if you want to catch that stream. If I'm gonna do it on Monday, I haven't decided yet, but it sounds like a good idea. I might do that. What's your Twitch? Twitch.tv/acegigma. There you go. Okay. Well, is there anything else? No more questions. Might do Blender stream on Monday then. Yeah. Okay. Okay. Oh yeah, all of my social links, if you want to follow me anywhere, then you can just go to my website. Or you can use the more fun link, that one. Both of these work. All right, I think that's it. Anything else in YouTube chat? Oh, any news on selling the gizmos? The gizmos, working on it. I think I have to learn Blender first, or Rhino, because I have to make specialized models of these that either snap together or have like vertex colors baked into them. After that, I need to do some test prints where I send it off to the printer company, and then they can send me the tests, and then I can verify and iterate. And then after that, depending on which model works best, then I can do a batch order and start selling them. So maybe soon. We'll see. Yeah, there's been a lot of pressure of people who want to buy my gizmos, so. Fusion 360 is good for stuff that's supposed to fit together. Isn't that expensive though? Isn't that like yet another Autodesk product? Rhino is probably cheaper, right? I'm getting really tired of subscription services, and Autodesk is just going full steam ahead into that, so. Educational version is free and they don't check student IDs. Can I claim an educational version as an educator? I don't know. Okay. Very good pair of kittens. Okay. All right. Oh yeah, I shouldn't hit 4 hours. Okay, we're far off. That's fine. All right. I think that's it. Hey, Salad. Stretch. What a tiny stretch. Thanks for joining. I hope this was useful. Oh, Oh, he's very long. Look at this boy. You're so long. You're so long, Salad. What a good boy. Don't you just want to, like, rub his belly? Sometimes a bad idea. Sometimes a good idea. But yeah, thank you all so much. I will still exist if you need to DM me or ping me in Discord. Don't hesitate to do that. Just remember that I might not answer immediately. I'm usually a very online person. Just don't expect me to always be available. But I will reply when I can get back to you. So feel free to. I prefer if you keep things in the public channels, because then you can also help each other, which is always good. Because quite often you learn a lot just by helping other people too. Being a teacher lets you learn yourself as well. Yeah. So thank you so much for joining. I will. For those of you on YouTube, yes, the VOD will stay on YouTube. It's going to be on my channel. So the next lecture is going to be on Tuesday. I might do my Blender stream on Monday, maybe. It's a fun project though, so I think I'm going to do that. But yeah, thank you all for joining, and I will see you all on Tuesday at least. So bye everyone. Good luck with all of whatever it is you're going to do over the weekend.